By data. Our next speaker is Radim, which is a great contributor to the Python language in terms of data perspective. He's also the author of GenSim, which is a very, very interesting library for Python. But I'm not going to do a lot more introductions because he knows far more than me. Radim?
Actually need the microphone. Can you hear me?
Yes, everything is recorded.
For the recording?
Yes.
Okay, so I'll keep it. Yes, so hello, welcome. Let me just see how this works. The topic of my talk today is, does Python stand a chance in today's world of data science? And the answer is yes. So, thank you for your attention. Let's go and have lunch. No, but really, what is today's world of data science? This is what I call the buzzword.
Topics. This talk is intended to be just an introduction, and I hope that is in the future you need to extend Python. At least you know the tools that are available and the basic examples. Also, my examples have been tested only on Linux and Mac, and with CPython and PyPy. But let's start. So, what's the motivation? Why should I write in C? I love Python. C is a bit of more difficult, more.
And there's also Python and the queues, and I'm not gonna go over all of that. So, and there's also Python, which we all like and love. So how does it fit into all this? Is it just like something for the academicians, or is it still relevant in the world? You know, there's Spark and all these new tools coming out all the time. We'll talk about some of that, but that's the main theme of this talk. Like, is it still relevant? I think that's a valid question, because a lot of things are going on. So, and this explosion of tools, it kind of reminds me of the Cambrian explosion, which is a biological term. It's an event that happened long past in the history of our planet, and a lot of new things came out. It was a lot of innovation, a lot of new life forms, and so on. So and it's kind of similar to what's happening now. You don't know where you stand, like there's stuff coming out every day, and you open a new blog post, and there's a new framework or a new language. You know how it works. Actually, this gentleman summarized it very well.
Overflows, interpreter does for us most of the cases, so another overhead. All the operators and operations are dispatched dynamically. So,
but the phylum is in biology. For those of you who don't know, you classify things hierarchically. So at the top you have kingdoms like animals and plants, and right underneath are phyla. So if you discover a new phylum, it's kind of big deal. It doesn't happen very often. And here he had so many of them that he was getting annoyed. And this is actually, you know, this is what happens to me too. Like I read a blog and not another data analytics platform. Not another database. Like, don't we have enough of them? So this is revolutions are good. I mean, this is a lot of innovation is going on, and it's exciting. Okay, this is a good thing. But at the same time, the landscape is so vast, and there's so many things that it's really hard to keep track. So it's hard to keep track of what's going on. So it can be also annoying. So that's another point. So let me check if this works. No, I'll just ignore it. There we go. So another question: what do I care? Like there's a lot of tools, but what does it have to do with me? So I run a consulting company. I started as I did my PhD in machine learning and so on. And I always liked building systems. So I worked in e-commerce for a long time, and I started consulting, and then actually started a consulting company. So I hired people, there's more of us, and we work on all sorts of problems for all sorts of companies. This is a few of them, and they range from small startups to normal businesses. And we also have some large customers like enterprise stuff, multinational companies with a lot of data. And yesterday there was a very interesting talk by Peter Coyle about deploying models, and it kind of made a point that data science and engineering are like separate things. At least that's how I understood it. That you should like hire different people for these different tasks. But the thing is, when you build solutions, you can't really separate it all that well, because the way you choose models for your solution depends on what kind of data you have, or what kind of infrastructure there is already. The customer has some data pipelines, the data comes in some format and at some frequency, you know, and the models need to be updated in some way, and that it restricts what you can actually do on the math side, on the data science, on the statistics side, and vice versa. If you have some special model that you have in mind, something that would solve the problem really well, maybe you have to suggest a new architecture. You have to choose the tools, the ecosystem around your math, your formula, so that it fits what you want to do. And there's actually a lot of demand. This is maybe a little surprising. There's a lot of demand for the type of services that we offer, which is these custom solutions. You would think, okay, you just put stuff in the cloud and people, you know, query it, and it's the end of the deal. But the thing is, a lot of problems and a lot of companies, they can't do that, and they can't do that because, one, they can't just send data to some, you know, random to the cloud. Can't do it for privacy reasons and IP reasons and so on. So that's reason one. And reason two, the solutions that are maybe in the cloud are too generic. This is again a concept that is, oh, that's Peter, hello. The solutions, you know, you wrap SVM and you do some predictions on the web, which is fine. But a lot of these companies, they have very specific needs, and for example, the one here, Brainspace, that's a company in the legal space. They do stuff with civil litigations and so on. So you need to have a pipeline, a protocol that is special, that you have to very carefully evaluate the confidence of your models. You can't just send something to the cloud and you get back, this is relevant or irrelevant, and then you present it to the judge, you know, because Alchemy API said so, so that's how it is. So this has to be customized in many ways. So that's another reason why not everything can be in the cloud. And then the final reason is performance, because sometimes there's just too many requests. You know, just putting something as HTTP in the cloud and running millions of queries, that's just not just costly but also slow. So they have their own infrastructure with their own caching layers. Okay, the way you draw metadata for the various records, they have their own systems for that. So you need to integrate more deeply than that. It's not enough to just deploy an HTTP server. So that's by way of motivation. So what do I care about this ecosystem? Well, I care because the customers, they're already sold on Hadoop, has very good PR. So usually they already have some infrastructure in place, and I need to know the limitations, how it works, you know, the various problems there can be, so I can design the solutions so they actually work. So it can't be separated all that easily. And in this talk, I'll actually talk about how Python fits in that. So there are a few points that are relevant, but the one that, you know, makes the headlines, it's not the most important one, but it's the one that makes the headlines, is the performance. So something is 4 times faster than the other thing, and, you know, that's what the technology people, that's where the heart is, the performance. So I'll start with that, but we'll talk about the other stuff as well. So just so this is not a, so I don't talk in too general terms, I prepared some examples for you. So this is not going to be about the math. So if you never heard about SVD, don't worry about it. It stands for singular value decomposition. It's a mathematical method that is used in various fields. You have a matrix, you know, a table of numbers, and you break it down into 3 other matrices. And why is this useful? I'm not going to go into that, but it's useful, for example, in genetics. Here, the slide I used, maybe you can't see, but here it says eigenassay and eigengene, so these matrices have special names in the domain. In natural language processing, they're called the latent vectors, so this is latent semantic analysis in the text processing world, and so on. PageRank is a special case of this SVD, so it's in the same domain as linear algebra. So that's a useful algorithm, and it's pretty old. It's pretty well understood, and it's in all the machine learning libraries. So we'll use that as a sort of benchmark to see how things do. And as the data set, what I'll be showing, I'll be using the English Wikipedia, and the reason is, it's kind of small. It's not a big data set, but at the same time, it's too big to be processed on a commodity normal little computer. So we need to use some.
Do you remember this init Newton? That is the first method that is called when a share library is loaded in CPython. Okay. So when I did grep, I ended up in this file into the CPython code. What it does is, okay, I try to load this share library in the path. What Python does is try to load a Python module. It does fallback, fallback, fallback. End up in trying to load a share library and end up here.
Actually, scikit-learn, which is a machine learning library for Python, as I'm sure all you know, it also is adding these out-of-core algorithms now. It's like a novel thing. I think in the latest release, they actually added incremental PCA, which is pretty much SVD. It's this algorithm we're looking at now, so I also had a look at that. And then there's one in Mahout. Mahout is like the scikit-learn of Java, the Hadoop world. Right? So it's a library built on libraries. And then there's one in Spark. Spark, I'll talk about it a bit later, but another of these new frameworks. It also has a built-in machine learning library called MLlib. So you don't confuse it. So let's get started. This is just the first data point, running this on GenSim. And in this graph, it's GenSim takes about, this red column is the memory too, like the peak memory. And it's about 3.5 gigabytes. And it took about 2.5 hours process to run the decomposition. Some number. In scikit-learn, it's more interesting to compare it with the others. So in scikit-learn, the memory was very similar. But actually, I realized when I was running this, they don't have optimization for sparse data yet, so they convert everything to dense vectors, which kind of kills the performance. So it's slow now, but I'm sure they'll edit later. But the point here is both of these are Python libraries, and it ran very well, like, no problems. It may be a bit slower because some optimization is not there yet, but no fundamental problems. It ran very nicely. So let's move on to the other one, to the Java one. Right. So
if you are writing extension for Python 3, there is some.
Fair number. That was a very beautiful talk yesterday about Spark. Unfortunately, it was in Italian, so I don't know what it said, but it was really a great presentation. So it's a project which is now under the Apache umbrella. And the gist of it is they put your data set in RAM, in memory, but this is distributed across the entire cluster. So if you have multiple machines, it's like you pull up all the RAM and you put the data set there. So that's like the main abstraction there. Underneath that, they also have an execution engine. So when something on the cluster it fails, you need to rerun it or you lose it, then it remembers how the data was computed, so you can run the same computation again. Which is more of a technical thing, but the idea is this is, MapReduce, it used to work like everything stored to disk, that's like the persistence, and then somebody figured out that's not a good caching layer, disk is not it doesn't give you good performance, so after a few years, they realized, and now this is in RAM. So one level of cache higher. I'll be using the latest Spark, which is 1.3 in what I'll show you. It includes this machine learning library called MLlib. So it's part of the Spark distribution. And since it's a framework for running on clusters, I'll run it on a cluster which is on AWS, Amazon Web Services, I'm sure all of you know. And so I use a very small cluster, it's a small data set, so I'll just be running on 4 nodes, 4 machines. Maybe M3x large, if it tells you anything, but it's and this is the result. So a bit disappointing. I was actually debugging this, and it's not a good, when you have a, and you want to show some comparisons, this is not what you want to show, but it turns out it's not trivial to fix it. It's like, as soon as the matrix, this is a traceback for you who can't see, so it didn't work. And I was trying to debug, so as soon as the matrix, the input matrix that we're trying to factorize, had more than 1,024 rows, items, it failed with some weird array out of bounds exception. Okay, so 1,024 worked, 25 didn't, so I don't know. I didn't really debug it more. I just looked into it in the sense that other people had the same problem. It's you know, this is not unique. But that's about it. That's where I stopped. What else? We have Mahalt. I already introduced it a little bit. It's more mature than MLlib. It's been around since 2008 or something. So a lot like scikit-learn actually, or Ginseng. So pretty mature, based on MapReduce. Actually, now that I looked at it again in the latest versions of them, they're moving away from MapReduce and they jumped the Scala, bandwagon. So that it now runs on Scala, and it's called that execution is called Samsara. So another buzzword for you. Most of them start with S, which is interesting. I don't know why. Very popular letter. So how did Python? How did Mahal do? There you go. Now, this was getting really annoying. PT job unsuccessful was the result of that. And again, I googled it, and people had the same problem, and again, no good solution. I tried in local mode because I wanted to give you something. It has another mode of execution where instead of a cluster, you run it locally. And that just ate up all my disk space, and then it failed because there was no more disk space. So, which I don't think is reasonable. It was like 150 gigabytes. You know, the problem is small. It's like 3 gigabyte dataset or something. You know, there's no reason to use up that much space. But that was the end of that. So I was unhappy. So I tried another one. This algorithm is called word2vec. It was originally so SVD kind of failure. Python wins. Yeah, let's just summarize it like that. And word2vec is another algorithm released by Google. It's pretty new. And why this is relevant is because it needs a lot of data. For those of you who don't know word2vec, you just give it raw text, a lot of words, without any annotation, just sequence of words and sentences. And it automatically learns for each word a vector. And then you can compare these vectors and say what is similar. Like these two words are similar. And you can even do a little algebra on the words, which was interesting. Like if you take the vector for king and you subtract the vector for man and you add the vector for woman, you get the closest vector to that is the vector for queen. So king minus man plus woman equals queen, which is what a human would do as well when you see the equation. So that was, and it has only raw data on the input, like no information about relationships and family ties or anything like that. So it's pretty fascinating, and for this to work, yeah, you need a lot of data. So that's the connection here to the measuring the scaling and so on. Maybe I'll show you later of that more, but now we'll be checking again several implementations. The original by Google, very neatly optimized, running on a single machine in C, written in C. And there's one in Ginseng, which is Python implementation. Actually, there's one in Spark as well in MLB, because this was such a, it made a lot of headlines, this algorithm, and it was released, so everybody tried to get a bit of it. So it's a good poster child for scaling. So there's one in MLB, and another one in a Java framework called Deep Learning for J. I'll start. I probably won't talk about this very much because I already had a talk about how I did the Python port. I did it at PyData in Berlin, and it's online. So if you want to see more details, you can check that talk. But basically, the original Python, like the raw re-implementation, was about 120 times slower than the NumPy implementation. I changed it to use vectors in NumPy and all the usual stuff. So it was 120 times speed up. But the fact is that the NumPy baseline was still 20 times slower. Sorry, I don't have the laser thingy, but
questo è l'endpoint di
Python because
it's not good. The training in C took you 1 hour with the C implementation, Google's original. Then the Python one using NumPy will take you like a day, which is not good. So then I optimized it more and compiled some stuff and did some other things. And I actually made it like 3 times faster than the C implementation with a good class libraries. It was nice, and at the same time, and it can be also parallelized. So on the same machine, if you have multiple cores, you can use them and get thank you very much. Great. So you get additional speedups. But this is still single machine. Both of them are single machine. You run on one computer, just use 4 cores. No distributed stuff. And the Python implementation is great, and this is another selling point for Python, that things integrate very nicely, as opposed to C, for example. So you can plug in on one end when you get the words, you just stream them through, so you can stream them through NLTK to get some other tags and do some other processing. And on the other end, when you have the vectors as the output, you can plug them into scikit-learn and do some clustering and so on. It plays very nicely together, and it's an efficient stream implementation. The results. The C implementation on that machine, on that EC2 machine, used about 2.4 gigabytes of RAM, and it took more than 4 hours to run. Data phone, that's where we start, optimized C, single machine. The Gen 2 implementation about the same time, much more RAM, about 6 gigabytes, more than 6 gigabytes of RAM. The reason why this is not faster is because of the BLAST library. It wasn't as good. This was just stock. I didn't do any special optimization or anything like that. But still, the time is about the same, memory a bit more. Moving on to the distributed world, Spark running on the cluster. In case you expected something else, something just, again, this is an exception, and something over to, like, the model was too big. It couldn't handle such a big data. Yeah, so, and again, I wasn't the first one to find it. This requested array size, whatever, people already had that problem, and it's known, it doesn't work. But here I was really frustrated. Like, I have to show you something. If I just tell you that, you know, Python works and nothing else does, you wouldn't believe me, right? So here I press on. I actually, what I did was I scaled down the problem so it works on Spark. So how that works in Word2Vec is there's a parameter that throws away some words, okay? And the parameter is the same across all the implementations. The value is 5, or whatever that means. And I actually, played with it until it worked for Spark. So I put like 100, so it throws away a lot of words. So the problem is smaller. And then Spark finished. Yeah, it didn't throw that exception. So that's what this graph shows you. And it took about 12 hours to finish on that cluster. So this is 4 machines. So actually, if it scales linearly, if we add 3 times as many machines, so 12 machines in total, then we should probably get to the same time. Yeah, so one single implementation, and versus a Spark cluster of 12, this should be about the same time if it scales linearly. I didn't check the implementation, but I assume it does. Which is pretty good, actually. I was expecting something worse. Like 12 machines, that's like the minimum size of any reasonable cluster. That's where you start. If you have something smaller, then it's just the cost of, and not just the financial cost of running the cluster, but the cognitive cost of keeping the maintenance, and you need some guy to do the operations and so on. It's all more complex, so it's not worth it. So the big players have clusters in the thousands of nodes. Dozens is like where you start. So this is actually pretty good. If you scale down the problem a bit, it works. Then the last one, deep learning for J, which is a Java framework.
TFFI, sorry.
Installing it has some special requirements. As I was installing it and trying to get it to work, all this config tweaking actually took me quite a bit of time to get all this working. It's not trivial, but as I was setting up deep learning for J, I actually got a message from David Tribila from IDEO, who is a very good engineer. He's also behind the Spotlight DBpedia editor, if you know that, for name entity recognition and so on. So they do some cool stuff at IDEO. And he was trying exactly the same thing, to build a framework to convert vectors, Wikipedia to vectors. And he was trying, of course, it was all in Scala, so he was trying first the Scala, the Java world libraries, and they all failed. And actually, he says that deep learning gets stuck in an infinite loop. So corpus. So I kind of stopped. I didn't want to waste more of my time. And in the end, he had to go to Python to use Gensim, in all his Scala framework, this Python library, because nothing else really worked. So that's another data point. Where am I going with this? These were just a few anecdotes. And I don't mean to say that these libraries are bad. Maybe it sounds like it from all the stack traces, but of course it makes sense to use more clusters to make everything more distributed. And this may be just, MLlib is a new library, so it's got it some slack. It's been developed, so it's a new thing. But this happens a lot. When I did another benchmark, I was looking for a library to do nearest neighbor search. I actually blogged about it. And there are a lot of libraries. This is a problem which is well known in the academic world for decades. It's pretty hard in high dimensional spaces. When you have one data point, give me the 10 nearest ones. It's also an important problem because it appears in all sorts of domains where you need to search for the nearest neighbors. So there's a lot of research behind that and also a lot of libraries behind that. So I wanted to choose which one is the best, which one should I use. So I did like a survey and some benchmarks again. This is what I imagined on the left side. This is the ideal before I started. So there's like a trade-off. I thought maybe some of them will be less accurate because you have to throw in some approximations to be really fast. So they will be fast but inaccurate, and some of them will be more accurate and slower and whatever. But what happened in the end was there was just one library that worked, which was Annoy. It's called Annoy. It's built by Eric Bernhardsson from Spotify, so this was released under Spotify. And the thing here was that they actually use it. It's a lot about the concept of dog fooding. You have to use it. If it's just an academic person who just is trying to build something scalable and publish it as the word count demo or something like that, it's not pragmatically useful. So I know it was useful, and from this side, I'll move to the concept of abstractions and APIs, which is what I really like. What I find that usually works is when the abstraction is very simple. Like, the more general you want to get, the simpler the abstraction has to be. Otherwise, it just collapses under its own weight. Like, it happens to so many frameworks. They try to do too much under a single rule, and the abstractions get too complex, and it just doesn't work. If you remember Weka from the Java world, like 10, 12 years ago, it happens a lot. And I think Python world has a cool spot here. I'm not sure if it's on purpose or because it's so fragmented that all the researchers and the science people they build their own libraries. But it has a lot of this stuff where you have single libraries that do one thing and do it well. So I think that's a bonus. This is just an XCase CD commit. All presentations have to have one. And this brings us to the Unix philosophy of do one thing and do it well. So I'm not like the first person to notice this, but if you want something to pragmatically work and not just the next big thing, keep it simple and keep the abstraction simple. Moving on to so that was performance. Makes sense in some cases, but you have to be careful how you use it. Like, you really need the cluster of computers to run something in 4 hours. Is your data big enough? This is a point of diplomacy as well, because when you have a client and they have that Hadoop cluster and they bought it and they have people managing it, and then you see what they actually do, you can't tell them like your data is small, just run a Python script, and you call it a day, or just load it into Pandas, and do the analytics there. Because when you say data is small, it sounds like data is insignificant, and nobody wants to hear that. So you have to be careful about that. But that's still the performance is. I wouldn't say like the biggest issue. Python it has great heritage of this high performance computing and going all the way back to these BLAS libraries and all the systems that were built in the past by very smart people and very smart engineers. So that's a plus. But there's other stuff that matters, I would guess, more in building solutions, and that's the stuff around the engineering stuff to make things successful. So it starts with How much time do I have? Yeah, enough. All right. So packaging. Like I don't know anybody who really understands this stuff with the set of tools and easy install and pip and wheels and X. It's pretty complicated. It's getting better, I guess. And a huge amount of work here is being done by Continuum Analytics, which is like the company fighting the world. As I'm sure all of you know. So it's an amazing company and they have all sorts of right vision for these tools, and they also have the experience to build it. So I'm really cheering for them. They're doing great work. If Python works, it's because of that. Because of Python data work. So a huge elephant in the room. Python 2 versus Python 3. I hear, when people don't use Python, when there are problems with the packaging, I hear a lot is like this divide, Python 2 versus Python 3, which one should we use? And I hear like it's Unicode and generators, but I don't think that's it. From my perspective, that's not relevant at all. Like Unicode in Python 2 is fine, no problems. Generators and iterators in Python 2, no problem. The reason why it's, at the same time, Python 2 is dead. The reason why you would want to use Python 3 is because of the new features, async I/O and type annotations and lots of small fixes and improvements. And that's the reason, not Unicode. And the reason why it's not being used, and it's not because none of our clients, ever use Python 3. It's when we develop open source, we do it in Python 3 as well, but that's like good manners. You should support Python 3. But it's the future. It's in the future. It will be used, and the reason it's not used now is because of the packaging and the deployment problems. Debian still has Python, I think 2.6, not even 2.7. So that's everybody has. Not true. Not true. Yeah, some older Python that is still Debian that is still installed in the real world, not the latest. And it's changing, of course. That will be improving. So and again, Anaconda and so on. Continuum Analytics doing a great job here. In the Java world, it's also not great. But this is for a different reason. They have a different sort of cultural approach to this. So once you sort out the class path stuff, the dependencies, it actually works well. That it's expected that you use a special type of environment with this integrated development environments, back loops and stuff like that. So once you sort it out, it's actually saying it's okay. An additional problem here is with the Java heap space, which you get a lot, which is usually fine, but in the distributed environments, it's kind of complex. You get a lot of, where does it actually come from? You have these workers, and you have the executors, and drivers, and main, and containers, and so which one is actually running out of space? Like which config? How do I find the right config for setting that? There's an additional problem here, and you come across this quite a lot. The Java heap space is a common thing. So it's not just Python that has problems with that. I think I'm running out of time a bit. So that was on the lowest level, like running a single library or a single problem. But what usually happens, you can't use a single abstraction for your entire solution. You can't write it all as coming Spark. Spark is a good abstraction. It allows you some operations, but some of them can't be done in Spark with not suitable abstraction. So you run bash scripts and Python scripts and all sorts of stuff. And how it usually starts is as a sequence, steps in a bash script and then some ifs, and then it gets really hairy. So there are tools that help you manage these flows of how things work. When something fails, the other thing shouldn't start. Some cleanup should maybe happen. Delete some temporary files and something else. And in this world, Java, traditionally, it's more enterprises, so it traditionally has a lot more mature ecosystem of managing this. But in Python, there are also a few tools, so it's not that bad. One of them is Luigi, again, by Eric.
Allora, in ogni pagina, questa è una checklist di Django.
Little pragmatic libraries, and if you need to improve something, you can do it yourself. Again, released under Spotify. I think it doesn't live there anymore now, but called Luigi. Then Pinterest released something called Pinball, which is pretty new. I don't know if any of you used it. I haven't yet. We used Luigi. We extended it so it can run Spark jobs. So on Pinball, I don't know, but also in the same space. Interesting tool. So Python is not really lagging here. You can't see this well, but these are like many tasks and they have dependencies, so it's like a graph and you know what to run when and what to do on something failed and so on. An important component if you know running things over and over. And logging. Logging sounds trivial and it's usually not the first thing, you know, when a new framework comes out, this is not what people ask, but it's super important, of course. Especially in the distributed environment where you have, you know, things are running on different machines, but how do you actually see what happened? Does it only log the things that happen in the main driver, or can you actually see the, you know, where it's actually running on the machine? How do you configure it if you want to see it? Do you have to go to that machine like SSH in there and search for the right folder? Or is it even being logged, or is the standard error just thrown away and lost? In the movement here is to use user interface for this. So there's like a little HTTP server, and you can see things visually. Trackers, but this is different for different systems. So Spark is improving here a lot, like in the latest release. Some other systems that are used, like Big, for example, not so great. If you want to work out what happened in a big script, you have to just hunt for the right job ID and find it in the job tracker and the user interface and whatever. And if you're using Python, the big screaming Python, it's even worse. And this is not only important when there's an error and you need to find what happened. What we also do a lot is we just sprinkle a bit of information into the log, like even when nothing went wrong. And this is really useful. Like, I know a lot of people just grab it for error and that's it. But a bit of like head, like the head command with Unix. Just print a few lines and you see what's going on in the pipeline. And we found a lot of problems like this which were not inside a single component, but outside the component boundaries. Like you expect, for example, you're sure that you're getting English text, you're processing English text, but then you print it and you see some Spanish. Is it a problem? Like, why is it just a quotation, or are we getting the wrong kind of data? And you really can't guard against all these things as a sort of unit test, because you would have to anticipate all things that could go wrong, but you never can. So that's why it's important also to check the logs and see the logs, have access to the logs. And is it configurable? Like I said, can we change the logging? Like, what if we want to log to our own database, put all the logs in a single place, like a central queue process them? Is that possible in the system we're using? And here, I think all the worlds are not very good. Python or the others, it doesn't make much difference. This is not a top priority for most of them, so it's usually a pain to debug these systems. You make the headline with the word count demo, and it runs very fast. But when something breaks, or you need to do something special, or you need to see something else, you find all the layers of abstractions and all. The more complex it is, the harder it is for you to know what's going on. The point of complexity. So how do we navigate the landscape? Like, there's so many tools. That's what I started with, and a lot of them are like this is the pufferfish. It's small, but it just puffs up, so it appears more important. And I see a lot of the new things are taking this approach. Like they sell you on the idea, and they hope enough people jump in to actually make it work. But I don't have the time to make it work. So you have to be careful where you jump. If it's just a pufferfish or it's a real project. It can be tricky to tell them apart, especially because in most of the tech world, most of the tools today, it's driven by Silicon Valley. A lot of stuff is going on there. And a lot of Silicon Valley is driven by greed. So by extension, a lot of the tech is driven by greed. That's my take on it. Like, why are they so immature and still so publicized as they will save the world? 5 minutes, right? So just be careful. That's my pragmatic view. I know a lot of everything about Spark is great. It's like every conference has a track about Spark and so on. But I just want to warn you that if you want to do a real project, not like a weekend where you just do your little thing, but something that should actually run in production, you have to be careful about these things and check the issues that people have and so on. So there's a lot of knowledge that comes into that. This is a summary, I think.
Inlines, non so se era una stack of inlines.
Maybe one point that, for me, when I decide for a project, shall we use Python or something else? For me, the selling point is Python really has this, some people call it baggage, like the scientific background it has. A lot of people from the outside see Python as a loose scripting language, but it really has roots in the scientific, very strong roots. So that's really great. It has a lot of good tools that make use of all the knowledge from the past, and a lot of experienced people who have built various types of systems, so they know how to design the abstractions and the APIs. It's not just some kid who's trying to make it big in Silicon Valley. It's really well thought out. Usually, a lot of stuff I talked about, but I have to finish now. So the last slide, if you remember, this gentleman from the beginning was complaining that there's too much new stuff going on. All the new files are being discovered all the time. But actually what turned out later as they got more fossils and more research into this, it turned out that it wasn't new phyla after all the time. A lot of the time they just had the skeleton upside down, or they had a fossil, only a part of a fossil, so later when they found the rest of it, they saw it fit together. It wasn't new phylum, it was just a part of something they didn't see yet. So it turned out there were not that many phyla in the end after all, and that's probably what happens in most of these revolutions, and this one as well. When the dust settles, there probably won't be that many new abstractions and new tools. Most part, caching in RAM on a cluster, it's a fine abstraction, but how many more useful things will there be? And how many just weird things, lags out of heads and stuff that won't live? So that's a question. I think Python has thanks to its long history and long heritage, has a very good chance. So I'm still putting my money on Python. But the main problem, like the annotations, it's difficult to maintain because of its duck typing, which is the strength, but also its main weakness in my point, and so on. But I think these things can be worked on, and because of the strong background that people have, and if it keeps being pragmatic, I think it has a great future. So that's my take on it. Thank you.
Any questions?
Thanks, Radim. That was a wonderful talk. I was recently reading the SciPy paper on Archive, which quotes your Gensim library, and they're talking about the abstraction and the clever abstractions chosen. Do you think that's one of the real strengths of the Python ecosystems? So I take scikit-learn with its estimators and its transforms and its predictors. You have all these containers. Do you think that clever sort of software engineering is really what makes this work?
First thing is Gensim, not Gensim. At this conference I heard NumPy, NumPy, all the different types of stuff. So I don't know what people use, but Gensim is Gensim, and abstractions absolutely. I mean, that's the hard part in everything is managing the complexity, so the interfaces you choose. And I don't think this is incidental. Like I said, I think it's because there's this heritage of solving real-world problems, that goes back, and you really run it on data, and you do need the results, and when you publish your paper, you do need to have the backing that actually works. So this is the reason why people have good experience with what works, and they can design the good abstraction, not just from the top of their head, like what they think should be done, but from actually seeing the data and knowing what should be done. So yeah, the abstraction. I don't know the paper you're talking about, but abstractions are pretty cool.
Are there any other questions?
Wonderful talk anyway, it's really interesting. And one thing, have you also tried using Julia for this kind of calculation? Well, SVD.
A little bit. What I would call the academic. Maybe if I shout. Okay, sure. Julia only has a little bit just to see how it works. I'm not expert in any way. But what is the question? Maybe we took the.
Have you tried to do the same kind of calculations? Well,
that's interesting. I mean, this was focused on Python and Java. Yeah? Java is like a big player there, and Python is the one we care about. But there's a lot of other stuff going on, like you say, Julia and Rust, and some of the tools. Like when I talked about the workflow management, in Python we have Luigi, Pinball, Azkaban in Java, and these other stuff. But there's also like a thing called Kitru, which is written in OCaml. I don't know much about it, but I think it's interesting that these ecosystems still exist. Because these people from different fields, they always bring something new, and even if it doesn't survive for all that long, it can influence the other solutions.
Thank you. Apart from Wikipedia English corpus, do you have some curious data set put in production with Jensim? Something curious to?
Well, usually cool things are covered by NDAs. Some of the companies were on this slide, so yeah, I can't tell you much. But Hearst has a lot of it. That's a company that has multiple TV stations and magazines and newspapers, and all that. So they have a lot of data, so that's interesting. Autodesk has interesting things. But it's not public. If you mean it like that, like do we have a public data set? No. That's why I choose Wikipedia here. You can download Wikipedia, run this yourself, and see if Radim is making this up or not. So I think it's a reasonable data set, and you can't find that many bigger data sets easily. So Wikipedia is like a compromise.
Anyone else? Any questions? All right. Thank you very much, Radim.